Hello friends, I am Amir Nizami, and today we are going to see the Mathematica Code for Zigzag theory. So some of my viewers have asked about the Mathematica Code, and if you remember that we have only touched the MATLAB code in the previous for the plate theory. I have done some Mathematica code for the beam theory, but not for the plate. So most of the viewers have asked about the Mathematica code, and they have also asked which one is more easier. So that depends upon the users that who is in regular use of Mathematica, then it would be more suitable. Otherwise, the MATLAB code, the person mostly use the MATLAB, so therefore most of the students use the MATLAB and they are most easily handling it. Okay, so that depends upon the person to person. So if you will ask to me that which one is more suitable, so for the analytical code, I used Mathematica most often. Otherwise, MATLAB is much better for the different type of codes like FEM and all. So for me, it's much handy for the analytical code. So today we are going to see the Mathematica code for the zigzag theory. So zigzag theory, that's the Sorrenti-D'Souza zigzag theory, which was the paper 2021. So if you go to the last lectures of the zigzag theory, so I have presented two types of zigzag theory there. One was the Sorrenti-D'Souza zigzag theory of paper I think 2021 published, and one was the Murakami zigzag theory. So today we are going to see the Sorrenti-D'Souza zigzag theory. So here we know that the stacking sequence. So there are four types of stacking sequence. That is a symmetric cross-ply laminate, anti-symmetric cross-ply laminate, symmetric angle ply, and anti-symmetric angle ply. So these four we can make analytically. We can code it. Otherwise, for the general type of laminates like 0, 90, 50, 30, any type of angle or any angle if you want, then we have to go for the finite element method. Otherwise, we can't do those types of lamination or general laminated skills with the analytical method. So we have to go for the finite element for that. So for these four cases, we can solve analytically. So we will see. So we will go to the Mathematica code, and first of all we will see symmetric cross-ply laminate. So here I have written the Mathematica code for the symmetric cross-ply laminate. So it is our symmetric cross-ply. Let me do it. So I think it's already written here. Sorrenti symmetric cross-ply laminate. So first of all, the length along x-axis is given for the plate 1.0 meter, and length along y-axis is also 1.0 meter. Means it's a square plate. Okay, and AX is the length along x, and I have just assumed by equals to length along y-axis. Substituted this value, and h dot 4 means a by h ratio, means length upon thickness ratio. So that is given here. Ax by 4 means this is the 4a by h ratio. So we will see, and the aspect ratio means length to thickness ratio, that is given here, aspect ratio, and the discretizing point is 17. So first of all we will see this is the 4 layer. So let's start with the it is symmetric cross-ply. So we will see. Okay, I think for the symmetric cross-ply laminate there is no 2 layer, only 3 or 4 layer we can solve. So we will see here 0.25 into h dot 4 means a by h ratio 4 it is taking considering, and 0.90, this I should delete, 0.90, 90, 0. Okay, let's see, and then the material properties here defined, Poisson's ratio. Okay, and the matrix, Q matrix for the bending, shear and all. So first of all we will run this code. Let's see what we get for this 4th layer. So I think we get this results, interface locations as this, QB matrix we are getting this, A B D matrix, E F H matrix, because for the zigzag theory we know there are A, B, D and E, F, H matrix also, and then AS matrix, that is a shear matrix. BC and DC matrix also we get. Okay, then the equations I have just printed and the results we got. So it's a symmetric cross-ply. So we know that there is no stretching part, means in plane stretching. So U naught and V naught is 0. W naught, theta x, theta y all are there. So UMN, VMN are 0. WMN is there. Theta x MN, theta YMN, psi x MN and psi YMN. That's given here. Now the results we can see the transverse displacements, that is almost 2.0 here, and that is constant throughout the thickness. So we know that in the zigzag theory, what we assume that the stretching part along the z-axis is 0. So that is, there is no stretching, therefore the thickness is constant throughout the thickness, not dependent on the z-axis, z coordinate. Then the in-plane displacement. So we can see that it is capturing the warping effects. Okay, so this theory, zigzag theory, is just because the name of zigzag is named on the in-plane displacements. As we can see, the displacement is like zigzag. Okay, so it's a mixture. So this displacements, in-plane displacements U. So for the various layers, the slope is changing, and this is called the zigzag. So that is the name due to this in-plane displacements. Now we will see its in-plane displacements V, means along the y-axis. Then gamma xz, that is the shear strain, gamma yz, and sigma xz. From the constitutive equations it is found. Then sigma yz from the constitutive equations. Then we are having the results of sigma xx. Then sigma yy, sigma xy, and these are the zigzag functions g11, g12, g21 and g22, and that's the derivative of that zigzag functions. And then from the equilibrium equations we get the sigma xz. From the equilibrium, EQ is the equilibrium equations, so we get these results. And zigzag sigma yz EQ, we get these results also from the equilibrium equations. So this we get for the symmetric cross-ply laminate for 4 layer. Okay, now we will read this output and we will see the next. I think let's do for one. Let us see some another case. Means it was symmetric cross-ply. Now we will see anti-symmetric cross-ply. So let's cut this and we will go to the anti-symmetric. The second one is anti-symmetric cross-ply. Okay, so we are going to see the anti-symmetric case, anti-symmetric cross-ply. Okay, so we will delete this output and we will run it again. So we will see here. Let us do for the 2 layer. First we will see the 2 layer output, and we will just comment it because we are running for the 2 layer right now. So we are seeing here we are having 2 layer and thickness is given when each layer is having 0.5 into h dot of 4, and material properties E1, E2, E3, G12, G23, G31, and theta 090 it's given here. So we will see we will run this code. Now we will see the results. So we are having the interface conditions here. ABD matrix is all, and then it's all the equations are also given here. We will see the way solve matrix solution and results. So here if you will see this for the anti-symmetric, we are seeing the anti-symmetric cross-ply. So in anti-symmetric cross-ply we are seeing that U naught and V naught is not 0, means UMN, VMN is not 0. because it's not symmetric case, it's anti-symmetric. So therefore, the stretching is also involved in it. Okay. Therefore, UMN and VMN is not zero as in the before case it was. Okay. So UMN, VMN are non-zero values. Therefore, this is the anti-symmetric case. So we will see this is the transverse displacements, and this is in plane displacement U, which is not symmetry. You can see from this side it's minus 2.5, while in this at the bottom end it's 0.5, or somehow it's greater than 0.5, means 0.8 or 9, like that. Similarly, V is also, it is also asymmetry. At this side it is 2.5, and on the left side it is almost 0.8. Then it is a gamma XZ, shear strain, transverse shear strain, gamma YZ, and the constitutive equations we are getting the sigma XZ and sigma YZ. Then we are getting sigma XX in this way. Then it is sigma YY, sigma XY, and these are the functions, zigzag functions, G11, G12, G21, and G22, and the derivative of the shape functions. And then it is the sigma XZ, transverse shear stress XZ, and it is obtained from the integration of the equilibrium equations. Okay. Similarly, this sigma YZ equilibrium equations we have got. This is by integrating the equilibrium equations. Okay. So these are the two layer. Okay. So now we will see 4-layer laminate. So let's comment it and comment, and then we will see let's do this 090 and 090. Let's remove it, it's not required. So it's also A by H ratio is 4 here. So we will run this code and we will see. So it's a 4-layer. You can see E1 is 25, 25, 25 all over. E2, E3, G12, G23, and theta is 090, 090. It's not 90, 0. Okay. Therefore, it's anti-symmetry. Let's run this code. So let's see the results. It's anti-symmetry. Therefore, we will see again here UMN, VMN are non-zero. Okay. And you can see the transverse displacements here 1.5. Then in plane displacements for this 4-layer is like this. In plane displacements V is like this. Okay. Gamma XZ, gamma YZ, then sigma XZ from the constitutive equations, sigma XZ from the sigma YZ from the constitutive equations. Then it's sigma XX. It is sigma YY, because it's anti-symmetry. Therefore, there is no symmetry around the mid plane. Okay, it's not symmetry about the mid plane. You can see it's different, and downward it's different. And this is sigma XY. And these are the zigzag functions, and hence from the equilibrium equations we get this transverse shear stress sigma XZ, and this is the transverse shear stress sigma YZ, and this we get from the integration of the equilibrium equations. So this is our second goal, what we have achieved. That was the anti-symmetric cross-ply case. Now we will see the symmetric angle ply. So let's see the symmetric angle ply. Symmetric angle ply. Okay. This is the anti-symmetric. I think it is not cross-ply, it's angle ply. And length along X, length along Y, it's also okay. Theta is 30, minus 30, minus 30, and 30. So 4-layer and symmetric angle ply laminate. Okay, and material properties are given here. Okay, So we can see Poisson's ratio and all. Okay, so we can run this code here. Let's see. Here it's ABD matrix, EFH. These matrices are given here. So we will see here UMN and VMN. These two are 0 here. Okay. Why it's 0? Because it is symmetry angle pi. Wherever it is symmetry only, then we will see that a stretching part would be 0. Okay. In plane stretching would be 0. Otherwise, for the anti-symmetric case, we have seen that it was non-zero. So whether it's symmetric cross-ply or symmetry angle ply, if the symmetry term is there, we will see that the stretching part would be 0. So UMN, VMN would be 0 always. Okay. Now let's move ahead and we will see the transverse displacement here. It's given. Then in plane displacements here as a zigzag we can see the warping effect. It's not linear completely, but it's a piecewise linear you can say. So one slope, then changing the slope, then again changing the slope. So that's why the zigzag effect is there. It's also V, in plane displacements V. Then the shear strain, transverse shear strain, gamma xg, gamma yg. Then it's the shear stress from the constitutive equations, sigma xx, sigma yy, and sigma xy, in plane shear stress. Then the shear zigzag functions, g11, g12, and then derivative of the functions. Then we got sigma xg from the integration of the equilibrium equations, and it is sigma yg from integrating the equilibrium equations. So now I think this is also we have seen. So we have seen the third case, that was symmetry angle ply, and now remaining the anti-symmetric angle ply case. So anti-symmetric angle ply case, let me see. Anti-symmetry angle ply. Okay, let's just starting. Okay, so this is the anti-symmetric angle ply case. Again we are taking the length along x and y same 1 a square laminate, and also a by h ratio is 4, and we are seeing for the 4 layer laminate. Okay, it's minus 30 plus 30 minus 30 and plus 30. Okay, for this layer if we run this code, let's see what we get the results. So ABD matrix all we get, and it's anti-symmetry. So what we remember that the stretching part would not be 0, means it would be non-zero, UMN and VMN. So let's see. Okay, we get this UMN and VMN as non-zero, so it's having some value. Okay, it's also having some value here because it's anti-symmetry, so therefore it is non-zero. And we can see the transverse displacements here, and it is in plane displacements U, in plane displacements V, gamma xg, gamma yg, sigma xx, sigma yy, sigma xy, and we are seeing this the sigma xg from the integration of the equilibrium equations, and this is sigma yg by integrating the equilibrium equations. So these two we get from the integration of the equilibrium equations. So I think we have covered all the 4 cases here, but we have left the sandwich case right now. Okay, so we will see that sandwich case we can see later. Okay, so I think we should close here. So thank you.